Okay, thank you, John, for your introduction. My name is Bernhard Moser. I'm coming from Austria, from the Software Competence Center in Hagenberg, which is a research and technology organization in the fields of software and data science and AI. And I'm very happy to be here to give a talk about ongoing research, which we're doing at SSEH. Which is going beyond the narrow AI of internet or IoT. Okay, and basically this is a status of two running projects. The first one is S3AI, which is a national Austrian project with about 4 million euros, more fundamental research, and the other one is the TEAMING.AI EU project on human and AI collaboration teaming. Okay, so before we had many breakthroughs and successful developments in the field of machine learning and so data-driven AI. Most of current AI systems are still narrow, and narrow means in the sense that they are fixed more or less to a static context, which means fixed to some predefined tasks. And also most of systems are of this way, like face recognition and so on and so on. So, and there are some major shortcomings with this. For example, in industry, and we in most cases we don't have big data. We are just have to face with limited data, and there are some problems with this. For example, data shift problems, or when it comes to transfer some predefined model for some situation and to transfer this to a new one, for example, for non-stationary environments, or what is also a big problem is to take into account constraints or some policies or rules. And of course, all the problems with explainability and interpretability. Yeah, in my presentation, I want to focus on the core problem of changing context in this setting. Yeah. In this context, I want to refer to a recent publication of our group at SSEH, which was published in April this year, about AI system engineering and a more systematic analysis and review of current challenges of such AI systems. Okay, when we are talking about context, we have to take into account context at different levels. At the bottom, we have to face distributions and shifts in the distribution, also shifts in the concepts. On the next layer, we have to face cope with policies, and on the very top, it's about integrating human and AI intelligence. I want to talk about the bottom layer. So this is directly related also of topics of the previous presentation. So it's addressing transfer learning and federated learning. Federated learning is just about distributed data sources, okay, and how to come up with a common model. But if the distributions in these distributed sources are not of the same, not exactly of the same, then we also have to deal with the problem of data shifts, and there transfer learning comes in. So, and just to illustrate the problem, what we have here is just an illustrative example here. Look on this problem here. We have some images which are labeled, so computer mice and bicycles. So it's the first context, first application, and suppose that we already have trained the model, and then we have a new one, a change context, with the same task, but with change context in the sense that the background is different. Yeah, and without any labels, we don't have annotations here. Yeah, the problem is, can we reuse the model from the first scenario to apply it to this one here? Is this possible? Okay, and this is the field in AI, which is called unsupervised domain adaptation. And the approach is here to map the data into a common feature space in a way so that the different distributions are aligned in some sense, and then to, so to say, to fuse the knowledge in the first one to the second one, to be able to distinguish also the classes in the second case. So, and from a modeling perspective, so this is an extension of classical machine learning. So we have the setting here. Of course, we have to minimize the risk to make some errors in the decision. That's a loss function, as we also have in other settings. But in addition, we have to take into account this alignment in this common feature space. So what this is done here, we start with a data space. Okay, with the data space, we have different distributions in the first and the second context. Then we are looking for some mapping. Often this is a neural network to map the data into some feature space where, so to say, we capture the common problem. Yeah, and this means to map this in a way that the distributions are aligned or become more aligned, the source distribution and the target distribution, but with restriction to preserve the distinguishing information to be able to separate the classes. So this is an optimization problem, or put it in mathematical terms, it's a regularization problem with two sub-problems. The first is to look for an adequate distance between these distributions, and of course this hyperparameter alpha has to be determined. So, and here it's also the distance matters, yeah. And did some results from our group at SCH where we came up with a robust one. We call it centralized moment discrepancy, yeah, and it's much more robust than other state-of-the-art discrepancy measures in this context. And another one, this is ongoing research. By the way, it's just reviewed now by Nurip's paper, where we have very, very promising results, not just doing it by ad hoc grid research to find out the hyperparameter, but by a mathematically based strategy. Okay, and there are many applications for this. For example, here it's in chemical industry. It's about some process industry for melamine production, and here the situation is exactly to transfer one model to a new situation where it has to be calibrated, where the model this very specific sensory system has to be calibrated to the new situation. So, and only a few data points are available to adopt it. Okay, now let's come up in our pyramid, yeah, and to look at the policies problem and the human integration problem, which is related to linked data and taking context into account. And for this, knowledge graphs are very useful because of their way that flexible, so data can be flexibly integrated. Yeah, and also knowledge graphs are also useful for encoding policies. Yeah, the problem here is that that knowledge graphs are much more designed for some static applications, and that in our industrial context, yeah, in our context of interacting with humans, we need it in a much more dynamic way. So first of all, and this is our teaming approach, we use knowledge graphs to model our static knowledge about the involved processes, about the team. Yeah, this means the skills of team members and interdependencies between them and workflows. And in addition, some policies, for example, about safety regulations or about ethical guidelines. So, but in our situation, we have to take into account dynamic data, which comes from sensors, from logging, or for example, from some feedback from the humans. And okay, now we have to face two problems. The first one is, in the end, we have to we need to make some decisions or some optimization and control strategies out of this. And for this, we need machine learning capabilities. So this is not directly inside the knowledge graph. Yeah, and so this is the first problem. The second problem is this dynamics. To be able also to handle some low latency decision problems. Yeah. So, and for this, the first problem, this is a standard technique in the meanwhile to map graphs and knowledge graphs into some vector space, for example, in 200-dimensional vector space, in the way that relational features are preserved. Yeah? And then on this vector space, one can again apply some deep learning methods and so on. So, and the other problem, this very, very crucial problem, and not easy to handle, is scalability and dynamics. And so, because most of the knowledge graphs as we have them nowadays are very time-consuming when it comes to updating. So, and there's we have somebody in our team, that's Professor Heiko Paulheim from the University of Mannheim, who is a specialist on constructing lightweight knowledge graphs and also lightweight embeddings. And yeah, and this helps us also to tackle the second challenge. So, and this is now an overall view of the TEAMING.AI approach. So we have as a base line some narrow AI, and now and as input, okay, machine learning, industrial IoT data, but we want to enhance this to come up in the end to integrate human intelligence, because human intelligence is somewhat complementary to artificial intelligence, particularly when it comes to integrating context. So, and this is the way how we approach it by utilizing knowledge graphs for all these sub-problems here. Yeah, so, and this is to come to the end, so to say, of my presentation. And if there are any questions, don't hesitate to drop me a line or put some questions here. So thank you very much for your attention.